Let's discuss the static characteristics of a system. The first characteristic is accuracy, which is defined as the difference between the true value and the measured value, divided by the true value. It indicates how close a measurement is to the actual value. Another important characteristic is precision. Precision refers to the number of distinguishable values an instrument can reliably differentiate. In other words, the number of significant digits in the measurement. For example, one scale may provide readings to the nearest 10, while another provides readings to the nearest whole number. The scale that measures to the nearest whole number is more precise. It's important to differentiate accuracy from precision. A measurement may be highly precise, producing the same reading repeatedly, yet still be inaccurate if those readings differ from the true value. In other words, precision does not necessarily imply accuracy. Other important static characteristics also describe system behavior. One of these is reproducibility, which refers to an instrument's ability to deliver the same output when the same input is applied repeatedly over a period of time. In other words, if you measure the same quantity multiple times, the results should remain consistent. Another characteristic is the input range, which specifies the allowable magnitude of input signals. As long as the input stays within this range, the system can produce accurate results. If the signal exceeds it, distortion occurs and the measurement becomes unreliable. Input impedance, defined as voltage divided by current, is also crucial. A high input impedance ensures that only a very small current is drawn from the source, minimizing energy loss. Since measurement sources often have limited energy, insufficient input impedance can load the source excessively and distort the original signal. For this reason, devices should have as high an input impedance as possible. Figure 8 illustrates the relationship between a system's input and output. When the input is 0, the output still has a non-zero value, known as the intercept. As the input signal increases, the output initially rises linearly. Beyond a certain point, the increase slows and eventually levels off, forming a plateau. In the linear region, the slope, given by delta y/delta xt, represents the system's gain. This is the method you will use in future projects. Apply a series of input values, record the corresponding outputs, plot the data, and determine the gain from the slope of the linear regression line. In Figure B, both the intercept and the slope change over time. These variations, called drift, represent inconsistencies in the system. Minimizing drift is essential to maintain accurate and reliable measurements. Linear systems are widely used because they follow two key properties. For a linear system, if an input x1 produces an output y1 and another input x2 produces an output y2, then applying x1 plus x2 will yield an output of y1 plus y2. Likewise, if the input is scaled by a constant k, that is, kx1, the output will scale proportionally to ky1.